This is a walkthrough of Further Maths AS Further Statistics 2 specimen paper. Question number 1. An antiques expert was asked to rank 10 china plates A, B, C, D, E, F, G, H, I and J in order of age. Her order was D, C, B, G, I, H, A, E, J, F, with D being the plate she thinks is the oldest. The actual ages of the plates in years are given in the table below. So we have the 10 plates here, A to J, and their actual age in the bottom row of the table. Calculate Spearmint's rank correlation coefficient between the ages of the plates and the expert's ranks. So first of all, just a reminder of Spearmint's ranks correlation coefficient here, and this is how we calculate it. So straight away we can write down that n is equal to 10. So what I'm going to do now is add a bit to the table where I write down the actual age rank and the judge's rank, where the oldest is going to be ranked 1 down to the least oldest or the youngest plate is going to be ranked 10. So starting with the age rank, the oldest is plate B, so that's going to be ranked 1. And then next is C, that's going to be ranked 2. And then we've got 110 after that. It looks like this one here, D, is 3. What I'll do, I'll cross them out as I do them, so I don't end up doing them twice. So I've done those 3. So next it looks like the one which is 85, so that's going to be 4, and then 80 will be ranked number 5, and then after that 75, so that'll be ranked 6, and then 7 here, and then 8, and then 9, and then 10. Then I'm going to do the judges rank. So number 1 was D, and then C, then B, then G is number 4, I is 5, H is 6, A 7, E 8, J9 and F10. So now we'll work out D, the difference between their ranks, the actual age rank and the judge's rank. So we've got -1, -2, 0, 2, 2, -3, 5, 0, -1, -4. Then we want those differences squared, so we've got 1, 4, 0, 4, 4, 9, 25, 0, 1, 16. So the sum of those differences squared, so is going to be 1 plus 4 plus 4 plus 4 plus 9 plus 25 plus 1 plus 16. That gives a total of 64. So now we can work out the actual correlation coefficient. So 1 minus 6 times by 64 divided by n is 10 times by 10 squared minus 1, and that gives exactly 101 over 165. I want to give that as a decimal, so 0.61212 recurring. So let's give it to 3 significant figures. 0.612, 3 significant figures. So it looks like there's a fairly strongish positive correlation between the judges' ranks and the actual rank of the age of the plates. Question 2. Charlie and Diane are trying to model the continuous random variable x. Charlie suggests modeling the cumulative distribution function, that's the CDF of x, with FC of X, where we have this CDF here. So for X less than 2, cumulative probability is 0. Between 2 and 5, including 2 and 5, the cumulative probability is 1, 6, and 9x minus x squared minus 14. And for x greater than 5, the cumulative probability is 1. Part A, explain what is wrong with Charlie's model. Now, CDF should be always increasing over a particular interval from 0 to 1. So over the interval 2 to 5, this function here should always be increasing. So we're just going to check to see if that's the case. So I'm going to differentiate this CDF, actually give me the PDF, and see where the peak or the trough of this quadratic occurs. So if I differentiate that, I'll get 1/6 of 9 minus 2x. So if I set that equal to 0 to work out where the flat point is, the sort of highest or lowest point, that will give me 9 is equal to 2x, which gives x is equal to 9 over 2. So that means that the highest point of the CDF is at x equals 9 over 2 or 4.5, and it should be at 5. So let's draw a little sketch out to show what this actually looks like. So here's my coordinate grid. So for x less than 2, the CDF is 0. So we're going to have a line going along here. And then we've got this quadratic, so it's increasing. And let's do the bit where x is greater than 5. So the CDF is 1. So it's going to be here. So what's happening is this is increasing like this, but at this point here, which is 9 over 2, we've got this peak, we've got this bump, and that shouldn't happen. It should just increase to 1, but not increase and decrease. Remember, it's a cumulative probability. So hopefully we can visualize and see what's wrong with Charlie's model. Okay, so Diane suggests modeling the probability density function, the PDF of x, with fd of x, where it's given by the PDF between 2 and 5, including 2 and 5, is k times by x squared minus 2x plus 2/3, and then otherwise it's 0, where k is a constant. Part B, what we need to do is to find the value of k for Diane's model. So we'll start with the fact that if we integrate the PDF between the limits of 2 and 5, that will equal the CDF, and that should be equal to 1. So our integration, let's put the k, which is a constant, on the other side of the integration sign over here. And so then we've got k x squared minus 2x plus 2/3 dx. We know that's going to equal to 1. So that's going to be k times by, so x squared becomes 1/3 x cubed. 2x becomes minus x squared, and 2/3 becomes 2/3 x, and our limits are 2 and 5. Again, that's equal to 1. So let's now put those limits in. So we've got k, and then the first, let's use some big square brackets here. So the first thing that I substitute in is the 5, so 1/3 times by 5 cubed minus 5 squared plus 2/3 times by 5, and then minus 1/3 times by 2 cubed minus 2 squared plus 2/3 times by 2, and that is going to be equal to 1. Just run out a bit of space there. So if we evaluate what's in the brackets, the first bracket will give us 20, the second bracket will give us 0. So we basically end up with 20k is equal to 1, which means that k is equal to 1 over 20. Part C, sketch f d of x for Diane's model. Okay, so here's my axes. I want to show the PDF between 2 and 5. So I've already substituted the values of 2 and 5 into this, where k is 1 over 20. So I know that when x is 2, the PDF is 1 over 30, and when x is 5, the PDF is 47 over 60. So just put a little dot there. It's going to be a quadratic. It's going to be a U-shaped quadratic. So between those 2 points, we're just going to have, I'll try not to draw it as a straight line, a sort of curved part of a quadratic, so something like that. So that would be my sketch of the PDF. I guess I could draw these dotted lines down here, because at all other points here it's going to be 0. So I've got that bit down here at the bottom. Part D, use algebraic integration on Diane's model to find E of x, the mean of x. So just as a reminder, this is the formula that we're going to use to find the mean. In our case, the limits are going to be 5 and 2, because elsewhere the probability is going to be 0, and then it's going to be x times by our function of x, and our function of x is 1 over 20, because we worked that out from the previous part, x squared minus 2x plus 2/3, and we want to integrate that with respect to x. So what I'll do here is take the constant 1 over 20 over to the other side of the integration sign, and then I'll multiply these brackets here. So I'll have x cubed minus 2x squared plus 2/3 x dx. So now we'll integrate that. So let's put the 1 over 20 first. And so the x cubed will become 1/4 x to the power 4. The 2x squared will become minus 2 over 3 x cubed. And the 2/3 x will become, well, we're going to have 2/3 divided by 2, so that's going to be 1/3 x squared, with our limits of 5 and 2. So now all we need to do is to substitute those limits in. So 1 over 20, and we'll put the 5 in first. It's 1/4 times 5 to the power 4 minus 2/3 times 5 cubed plus 1/3 times by 5 squared, and then minus 1/4 times 2 to the power 4 minus 2/3 times by 2 cubed. That doesn't look like a 4, does it? Let's do that again. Plus 1/3 times by 2 squared. Okay, so evaluating that, we'll get the 1 over 20 outside the brackets. The first bit we've substituted in 5 becomes 325 over 4. The second part here we've substituted in 2 becomes 0. If we multiply that out, that becomes 65 over 16. So I guess we could leave our answer like that, or we could give it as a decimal, and we don't really need to round this. 4.0625. So either one of those should be fine. I can leave my answer exact, so I'll actually leave it as the 65 over 16. Diane is going to calculate the median of x. Part E. With reference to the shape of your sketch in Part C, and here's my sketch here, state, giving a reason, whether or not she should expect the median of x to be smaller, equal to, or greater than the mean of x, E of x. So the first thing, looking at the shape of the sketch, shows us that this is a negative skew. You can see because the probability mass is sort of bunched up, more of it is towards the right hand side. Now when we've got a negative skew, we want to know which one is bigger, the mean, the median and the mode. And my little trick is write the three words out in alphabetical order, and negative skew is telling us to use the less than symbol like this. So the mode is going to be greater than the median is greater than the mean. Now we've worked out the mean in part A, 65 over 16. I think I wrote down that was 4.0625, something like that. So that I could write under here 4.0625. And the mode, well, we need to find the highest point of the sketch, and that's at 5, so the mode is 5. And already I can see, well, the mode is greater than the mean. The median is going to be somewhere in between because it's a negative skew. So we can finish off by saying, so the mean is less than the median, it's less than the mode, that's a negative skew. Therefore she should expect the median of x to be greater than e of x, the mean. The median of x is greater than the mean. So that's the word that we're going to be looking for. Question 3. A piece of string AB is 7 meters long. A point P on the string is chosen at random. The random variable x representing the length AP has a continuous uniform distribution over the interval 0 to 7. A rectangle is formed with length AP and width BP. Find the expected area of the rectangle. So over here, just a quick reminder of the mean and variance formula relating to a continuous uniform distribution. Then what I'm going to do over here is draw a sketch of this rectangle. Okay, so we have this piece of string and its length is 7, and then it's basically folded somewhere or bent somewhere to form like the two sides of this rectangle. We know that A to B, its length is 7 meters long, and then this point P is chosen at random. Now if we call the length AP x, because x is going to represent the length of that side, then because the total length is 7, then the length of the other side must be 7 minus x. So the area is going to be x times by 7 minus x. So we'll start by writing down our model, and that is x is uniformly distributed over this interval 0 to 7. So then we'll move on to say how we find the area. So the area, if I expand the brackets, is going to be 7x minus x squared. That means that the expected area, the thing that we're trying to find, is going to be equal to the expected value of 7x minus x squared. That can be split up into the expected value of 7x minus the expected value of x squared. The 7 from the 7x is basically 7 lots of the expected value of x, and then minus e of x squared. Now e of x squared we can't calculate directly, but it's going to appear in the variance formula, because remember that the variance of x is equal to e of x squared minus the mean squared. So we can use that to get this e of x squared part. So we're going to start with the e of x part, 7 lots of e of x. So let's do that over here. So 7 e of x is going to be 7 times by, and we can just use the formula here, a plus b. So that's going to be 0 plus 7 all over 2. So that'll be 7 times by 7 over 2, or 3.5, giving us 49 over 2. Okay, so that's our 7EX part. Then we'll move on to the second part, which is the subtracting the E of X squared. I guess what I'll do, I'll highlight this answer because I will need that toward the end. And so I'm going to rearrange this variance formula to get E of X squared. So E of X squared is going to be the variance of X plus the mean squared, so E of X all squared. So we'll start with the variance of X, so that's going to be B minus A over 12. So that's going to be 7 minus 0 all squared, over 12 plus the mean squared. So the mean is that 7 over 2, not the 49 over 2, because that's what we got when we multiplied it by 7. So this part is E of X. So we're going to put here 7 over 2 all squared. And that gives a value of 49 over 3. And we'll highlight that. So our expected area is equal to, and we'll go back to this formula over here, 7E of X, which was 49 over 2, minus E of X squared, which was 49 over 3, and that gives 49 over 6, and that'd be centimeters, meters squared, isn't it, because the length of that was 7 meters, so meters squared. So I can leave my answer like that, or give it to 3 significant figures, which I think would be something like, because it's like 8.1666 recurring, so 8.17 if we did decide to go for 3 significant figures. Question 4. Nazir is studying the hearing function of workers in his factory. He takes a random sample of 10 workers, let's underline that, sample of 10 from his factory. He records their hearing function as a percentage H, where 100% indicates perfect hearing. He also records the number of years they have worked in the factory W. The results are summarized as follows. So the mean of H is 86.5, the mean of W is 10.5, SHH is 198.5, SWW is 470.5, and R, the correlation coefficient, is equal to negative 0.620. Part A, stating your hypothesis clearly and using a 5% level of significance, test whether or not there is evidence of a negative correlation between hearing function and the number of years worked in Nazir's factory. So for a test for correlation, H0 is always that rho is equal to 0, and since we're testing for a negative correlation, it's going to be rho is less than 0 for H1. So we need to look up our critical value from the formula book, and that's going to be for a 5% level of significance, and N is going to be 10, that's our sample size, and that gives a critical value of 0.5494. I'll draw my number 9, put on the critical value, and I want the positive and the negative of this, so 0.5494, and then over here negative 0.5494. Okay, so my critical region are these two bits at the end. I'm going to see where my calculated value of R is going to be. So that's going to end up actually in the critical region, isn't it? Yeah, so that's going to be somewhere over here. So we can say that since negative 0.620 is less than negative 0.5494, it is in the critical region, so therefore we reject H0. So there is evidence of a negative correlation between hearing function and the number of years worked in the factory. So I'll just put number of years worked and finish it there. Part B. State why your test in Part A is consistent with the use of a linear regression model to describe the relationship between hearing function and the number of years worked in Azir's factory. Now, because we rejected H0, that means that the result is significant. Therefore, it is consistent with a linear regression model. Nazir wishes to estimate the effect that the number of years spent working in his factory has on the hearing function of his workers. He decides to create a linear regression model. Part C. Using the above data, find Nazir's linear regression model. So a linear regression model is going to be of the form y is equal to a plus bx, where x is our independent or explanatory variable and y is our dependent or response variable. Now in this case we're talking about hearing function and the number of years working in the factory. The length of time working in a factory is what's going to affect the hearing, not the other way around. So the independent or explanatory variable is going to be the number of years working in the factory. So I'm going to replace the x with w, the number of years working in the factory. That is the explanatory or independent variable, because that affects the hearing. So the dependent or response variable I'm going to replace with the letter h. So this is going to be my linear regression model. So we're going to start by calculating B. Now in the formula book it says the way that we calculate B, it's sxy over sxx. So if we basically replace x and y, remember the w was x and the h was y, we get swh or hw, just put them in alphabetical order, over sxx, and that's going to be sww. Now out of those two I have the sww, and the sww is 470.5. I'm going to have to calculate the shw. Now to do that I can use the residual sum of squares formula, which is in the formula book. So I'm going to do a similar thing again where I swap the y's for h's. So I'll do that now. So all of the y's, I'll put an h there instead. And then where I see x's, I'm going to put w's. So I need to put h here and h is here. And then for those x's, I'll put w's there, like this. So this is how I'm going to use the formula. Now the bit I want to find is the HW part here. All the other bits I know, so I can just substitute those in and then rearrange. So let's do that now. SHH is going to be 198.5 minus the SHW, which I want to find, all squared, over SWW, which is 470.5, is equal to 198.5 times by 1 minus r squared, and that's going to be negative 0.620 or 62 squared. So rearranging that formula, you'll get SHW all squared is equal to 188.5 minus 188.5 times by 1 minus 0.62 or 620 squared times by 470.5. So that will give me SHW is going to equal the square root of that, and that is 189.47493. I think it's at 16. So that's the number here, the exact value that I'll be using up here. So I'll just write that down, 189.474 and so on. Now, since this is going to be a linear regression for a negative correlation, that means that this value here of the gradient needs to be negative. So when I work this out, I need to make sure that I put a minus sign in front of it. So since negative correlation, B needs to be negative. So it's going to be minus the result of this calculation, which gives me negative 0.4027 and so on, 09. Now we're going to move on to finding the value of A. From the formula book, that's equal to the mean of Y minus B times the mean of X. Changing that to the letters that we're using, A is going to be the mean of H minus B times the mean of W. So we've got the mean of H and the mean of W, so A is going to be equal to 86.5 minus the B that we worked out, and that's going to be the negative 0.4027 and so on, and that's times by the mean of W, which is 10.5. So using the answer button to be as precise as possible, I get A is equal to 90.72845 and so on. So I have my values of A and B here. So here's my B, here's my value of A. I'm going to give my values to 3 significant figures. So I can write down that my linear regression model, and I'll write it here, H is equal to A. So that's going to be 90.7, 3 significant figures, minus B, so that's going to be 0.403 to 3 significant figures, W. And I'll just put down A and B are 2 3 significant figures. Okay, moving on to part D. Use this model to estimate the effect of hearing function of working in the Sears factory for 5 years. Okay, so that's going to be H is equal to 90.7 minus 0.403 times by 5. So that gives 88.685. Now I can see from this linear model that we're starting from a baseline of 90.7% hearing, because at no years H would be equal to 90.7. So I want to work out the difference between that 90.7 baseline minus what it's going to be over 5 years. And that gives 2.015. Okay, so we're talking about a loss of 2.02% hearing loss, and that's given to 3 significant figures. Okay, so let's just highlight that answer before we move on. Part E. calculate the residual sum of squares for this model. Okay, so to calculate the residual sum of squares, we've got two ways to do it, by using all of these summary statistics here, or by using one of the summary statistics and the value of r. I'm going to use the second way because that looks a little bit easier to work out. I could do it either way, I'll get the same answer. So our residual sum of squares is going to be equal to SHH, which is 198.5, times by 1 minus r squared, so that's negative 0.620 squared. Let's see what that gives us. And that is 122.1966. So I'll give that to three significant figures, 122. And the lower this value, the better really our regression model fits the data. So we get 122. Part F, what does it say just before part F? Erica was one of the workers included in the sample. She is 58 years old and has worked in the factory for 10 years and her hearing function is at 80%. Part F, calculate the residual for Erica's data. Now to calculate a residual, we take the observed value and we subtract the calculated value. In this case, the observed value, the observed hearing function was at 80%. And we're going to subtract from that our calculated hearing function. Just as a reminder, the formula that we had from part C was H is equal to 90.7 minus 0.403W. So we'll have in brackets 90.7, this is going to be our calculated value, minus 0.403, and Erica's been at the factory for 10 years. So we're going to times that by 10, and we get a negative residual of 6.67. Okay, let's continue. A friend visited Nazir's factory and suggested that all new workers should have an assessment of their hearing function when they start working in this factory. Part G, two parts to part G. First part G, state, giving your reasons, a limitation of Nazir's current model. So one limitation might be this: there is no baseline test. So what that means is, what was a person's hearing function when they started working at the factory? You could have somebody that joined the factory and their hearing was already quite poor anyway. So we need to know what their hearing was like at the start. And the second part of part G, explain how he could use this extra information to design an improved model. So a possible improved model could be that with a baseline test, he could measure the change in hearing function rather than just the hearing function itself. So looking at the difference in somebody's hearing over a number of years rather than just, well, what is their hearing function? So comparing it with some sort of baseline test, some baseline information.